Okay, we are Group A and our topic is CubeSafe. Okay, this is our outline. The first four topic is about the solar panel, and the sixth topic is about the load because the paper about the loads is fewer, so we are more focused on the solar panel. Yes. And topic 7 is about the Gantt chart. It's about our timeline. Yes. And the first topic is about two types of how to install the solar panel. And first is body mounted panel. It is strictly stick the solar panel on the body. And actually the disadvantage is it is limit surface because the size of the CubeSat is limited, so it only can the maximum size is to fit the size of the CubeSat. Yes, and but it is simpler than deployable panel. So this is simpler, but this one is it is harder to design, but it can have more power to have more power to yes. So the advantage for this one is larger surface and higher power generation. Yes. And the second topic is about two type of deployment system. The first type is called ISIS POD. It is developed by innovative solution in space, and this kind of deployment system can afford a three-stack solar panel about a deployment solar panel. And this one is developed by California Polytechnic State University. And this one is more famous, not famous, it's usually use this one to deploy the the CubeSat, but this one can only afford two static solar panels. Yes. And this two is this one is longitudinal solar panel axis, but these two have the different advantage and pros and cons. And this paper choose the longitudinal for their design because this for advantagement. The first one is less disturbance talk during deployment because this one is more closer, so it maybe have some crash to while folding a solar panel. But this one there are two hinges here, so actually these two hinges have less chance to crash each other. Yes. And second is less moment of inertia because moment of inertia is BH cube over 12. So this one have less edge. So this one have less moment of inertia. Yes. And third point is I just said yes. And four is there are more space to installation because there are it has two hinges and the hinge is here and it maybe have more crash here. It's also the problem of hinges. Okay, next part.
And the third part is deployment of mechanism. So to unfold the solar panel, the design is two hinge and two thermal cut. And we will introduce the thermal cut on the next slide. And for the hinge, The main hinge allows the entire assembly to rotate 90 degrees. And the second hinge allows the panel to rotate for 180 degrees. And the panel is deployable. They are fixed with the nylon yarn, and the thermal cut can hit the nylon yarn to cut the nylon yarn so the solar panel can unfold. And the next topic is vibration reduction system. The first is the flat spring retention system. The system can prevent micro vibration during the flight. And second is the viscoelastic multilayer system assembly. And the solar panel is designed by PCB. So when it launches, the vibration may cause some damage. And through this VMLSA, it can reduce the vibration during the launch time to the space.
Next topic is about deployment trigger mechanism. So in the slow state, the solar panel is secured with the bracket and dyneema wire, and then an electrical interface. PCB sends the electrical current to the resistor when the deployment is triggered. Then the resistor is heated up and cut the wire. Once the wire is cut, the focal pins push the solar panel outward, while the hinge torsional force deploy the panel smoothly. The system has been repeated tests to proving it stable and reliable for a low mission space.
And this part is for notes, because CubeSat are typically launched into space using launch vehicle. So some satellites, small satellites, would assemble together to be launched to the airspace, and they must withstand various mechanical force and loads, and also we need to consider about the environmental conditions during the launch. So first load is static acceleration loss. It may be induced by the launch vehicle's propulsion system, and it also would vary throughout the launch processes and may cause the structural failure, and it may crack during the process. And second, sinusoidal vibration loss. It is resulted from interactions between the vehicle's natural frequencies and the CubeSat structure. So it occurred during the initial launch stages and can cause resonance issues. And the third is random vibration loss. It is caused by the acoustic noise and the pressure changes. And it is characterized by unpredictable nature, measuring using the ASD, which is acceleration spectral density, from 20 Hertz to 2000 Hertz. And these kind of loss may lead to potential long-term fatigue. And fourth, shock loads. It is resulting from the instantaneous impacts during ignition and separation phases. And because shock loads has a high acceleration, like up to this huge number during the short duration, and so it requires a strong design to withstand this kind of force. And so we picked two of them as our examples. First is static acceleration loss. So during the initial ascent, CubeSat may need to face the continuous acceleration when the rocket is lifting off, and so the rocket accelerates at about 3 times the force of gravity. So the CubeSat must to be designed to withstand this kind of load without structural failure. And second, shock loads. So when the rocket's engines ignite, the southern shaft can create a shock though on the CubeSat. So, for example, if the CubeSat is subjected to a brief and extends shock about 50,000 meters per second square during the phase. So this kind of structure, material, and components need to be designed to absorb and withstand this kind of high impact forces without damage. And this is our game chart. This is our timeline about what we are doing this 6 weeks. Yeah. Okay. Okay.
Sorry, there are one more point we forgot to mention. Like, because actually this is our focus paper. We designed the solar panel by this one, but this one is about another paper, and this one actually is for one unit CubeSat. But I think we think this design is very useful, so we choose to maybe it can apply for our design. And this one is also the one unit CubeSat design, and this one is for the 6 unit CubeSat deployment trigger mechanics. And we think these 3 designs maybe can combine to our design. So we choose these 3. Maybe it can aid in our design. Yes. Okay, that's our presentation. Thank you.
Let's give a applause for the presentation. So, what will be your basic size of the CubeSat?
3 units.
3 units. And why you choose the lateral deployment instead of any other origami features like Chinese fan or something new? You can use a Chinese fan, it's like opening with a circular. Something, because when we start our last presentation, we talk about like origami. So, have you gone to some papers which they use origami to unfold the? This is a general mechanism. Which
Yeah. We found many solar panel for CubeSat, paper for CubeSat, but the most paper for the solar panel is they use unfolding. Yeah. So I didn't see the
But you
paper
can
about
try.
the
This is a project, so you can try with something new.
Yes, I think so. But I think this is not the.
Like there will be no actuator. Like you can try and you can compare that they are like they are using actuators. But if you can try, there is just because right now the solar panels can be we are flexible solar panels are available. So it's just a flexible. So just like a paper, you can fold it and just you can release the rod and it will automatically open. So no need of much actuators, which you are showing in. Like in mid, you have so much of actuators to open. So to reduce these actuators, you can suggest something which can be foldable and just open it. That's why a professor suggests you to, in initial, we suggest that use some origami to open it. Also, how you will do the CFD analysis or enhances, what load analysis you will do? Some analysis you will do?
Analysis of
Like mechanical analysis,
yeah.
something?
So after building the 3D model, we will use answers.
So, but what type of analysis?
What type?
Have you, because if you design something, there are 2 conditions in CubeSats. One is the launching condition, which have the gravitational force, and another is microgravity in space.
Yeah.
So how will you do
focus
that?
on the launching process. The force, like what I mentioned, force the 4 loads in our slides will do analysis on this.
But I think if you can suggest something without actuator unfolding of the panels, like actuator free, it may be a weightage to project.
Okay.
I think it makes sense that we should reduce the actuators. Will you show the slide? Yeah. Like here there are, you have actuator, the green one are the actuators which unfold the panel.
Yeah.
So if something will be like, it's a packed, and because we don't want a solar panel to be open in the launching.
Yeah.
It will be open in the space. So only one time opening is that. It is not every time you fold it or unfold it. Like satellites is like that. When you launch it, it will be on the destination. Then it will unfold its solar panels and start working. So maybe you can propose like this is the general method which someone has done. Maybe now you find out how to fold it, and it can be like one actuator and it will just open it.
Less the number of actuators.
Yeah, so less the number of actuators. I think it will be a good one. You can just suggest it and maybe you can find out. I mean, there are various origami methods. You can just find out how to unfold a paper, and with the size you can just redesign it that it will be automatically unfold with the mechanism because they are flexible, and you release it, it will unfold it. So there will be no actuators to open it. It will be a good suggestion for you. And also you have to calculate something with like loading, because you first you have to design the 3D model. Then you have to interact with which are the conditions where is your deployment system will be placed. So everything will be in focus, and how because these satellites are launched and it has to be in position. There will be also some thrusters. So you have to check the design properly. Because the main focus is your deployment system and the solar panels. It's your main project area.
Yeah.
What's your main project focus on?
The first one is about deployment,
Mainly the deployment
Yes.
of the solar panels and the design of the solar panel deployment system.
yes.
So you have to also check that for 3 unit, how much solar panel surface area is needed to power. Because that is the main reason. Otherwise, you are 3, you can have 5, 6, 7, 8, 9.
Yeah.
So how much is needed for particular deployment? How much surface area to power that that satellite? So that surface area is important.
Yes. Okay.
Because without surface area, how you can deploy something?
Yes.
So your surface area is important part of design. So find out some papers where there is a surface area with respect to the solar panel, with respect to the size of the CubeSat.
Okay. Thank you.
So the next group is group B. Group B, everyone is present? Have you seen the AMR? Have you seen the AMR?
We already see the CAD design.
The actual design,
we didn't have it.
I already told you that ask the TA and go to Industry 4.0 and at least you can have a look.
I think by looking at the CAD design, we know like
But
how
you,
exactly.
it's a physical, so that you can know what you want in the mind is.
Hello? Hello everyone, we are Group B. And before we started, we need to know the problem of this robot. And the problem is the total weight is too heavy. It's about 1,690 kilograms. And it will break the floor. And the load of the middle of the basement is too large and it's unsafe. Previous people try to increase the wheel or metal bolts, but it's not working. It still will breaking the floor.
So this is a solution we think of is to change the wheel unit to a continuous track. So we think of the advantages of a track is that the surface area of this part, which contact with the floor, is way much larger than the wheel itself. So the pressure displacement is more average. So it will not have like a very concentrated force on the floor. So it will not break the floor. And the second part is it have a more stable plate, so it will not tilt when the robot arm maybe like pick up something very heavy. And the third part is compared to the previous wheel is this one, the one on the left bottom right. This wheel is called the Magnum wheels. Compared to the Magnum wheels, because the Magnum wheels is like two cylindrical pointing at each other, so the momentum efficiency is actually kind of bad because there's like force and they're pointing towards each other, so the momentum efficiency is very bad. So compared to the track unit, which can have like a very significant improvement. And for that part is this track unit is very cheap and very easy to maintain. And the disadvantages we think of is because that wheel can have like a finer control, so the robot will move like very precisely. But I think this part is can be compensated by the arms, because when we're moving the track unit, we can just move like maybe there's like a arrow of maybe 10 centimeters. It can be compensated by the arms. We just have to make more adjustment on the code and let the arm do the adjustment. So this can be compensated by the robot arm. And the part is that it might add up more weight to the whole system because by supporting the track unit, we need to add more wheels, and there's have to be more shaft needed. So we might end up with more weight, but the weight is displaced on the more surface on the floor, so it will not break the floor by doing that.
So now I wanna talk a little bit about a comparison between wheels and tracks. We know that the thrust developed by a system with gear is the integration of the shear stress over the contact area. So if we have a lower shear stress and lower contact area, it will lead to the lower value of thrust. However, on the other hand, a lower total contact area with a lower contact area, the average normal pressure under the tires of a wheel will be higher. So this leads to the conclusion that tracks are better at decreasing distributed loads and reducing ground pressure, making them ideal for a soft and sensitive terrains. However, wheels are more efficient and suitable for hard and firm surface where load distribution is less crucial. In this case, we consider all the conditions are the same, but we want to get rid of breaking the floor, so we think tracks would be a better solution in this case. That's all.
One? So you are replacing the Magnum wheels with the track.
Yes.
So what about the degrees of freedom?
Because there's like the base of the arms have like a 360-degree
No.
turn. No.
Base of arm is useful for front load, and okay, you have a 3D, but that's why there is a controller box. So you cannot use this side, but the Magnum wheels can easily rotate 360 in their own place.
So there is
a rotation.
There's
You
no
can
like
move X, Y, and Z axis.
there's no like a motor on the bottom arms.
No, there is a motor on the arms, but you cannot compensate everything together. Every time you cannot move arm back, then your error compensation will be more high. So that's why I'm asking, what about like if I want to rotate the vehicle, how your tracks will be behaved?
Can you say that again?
If I want to rotate the vehicle, how the tracks will work
The track.
for rotation?
You mean like
Yeah.
turning? So one will like move this way and one will go here.
It
So
will rotate.
you will turn. Like you can like go around.
So you will redesign the chassis with track
Yes.
and put the robotic arm and do the structural analysis for that.
I think we'll just yes we'll put the tracks on the chassis and then we will analyze the shaft of the track unit and also the track.
The track,
Yeah.
the frictional force between the ground and the track.
Yes.
That's my question is like how you can move whole body, because there are lots of small wheels on the track. So how much motors you need
We
to
haven't
drive the shaft?
we haven't
Calculated all this.
calculated like how much goes thrust we have to have for the.
But what is the general advantages of using track instead of Magnum wheels in indoor environment?
professors don't want to break the floor, so I think this is the solution.
No, but what is the general, general advantage? Like, have you go through some research view, some
Yeah.
review, that you will find that the tracks are good than Magnum wheels? Is any paper suggest like that?
We didn't find a paper specifically for the Magnum wheel. We find a lot of paper just compared to like a rubber wheel, just like a normal wheel, but not the Magnum wheel because we haven't find like.
But the problem here is with the weight which is in the center. You know, in the center of the chassis we have 4 wheels to support. To avoid the buckling, we have 4 small wheels, and that is creating the flow damage, not the Magnum wheels.
Yes.
So this track will reduce that 4 wheels, which are in the bottom.
middle.
Yeah.
Yeah, I think
The first
so.
problem is not the Magnum wheels.
Yes.
The problem is the small wheels
In the middle.
in the middle,
Yes.
which supports the frame. That wheels are creating the flow damage, yeah, not the Magnum wheels. Magnum wheels are okay.
Yes.
So how this track can avoid you, it can eliminate the 4 wheels. That I want to know. Have you thought about that? Or you thought that the Magnum wheels are creating a flow damage?
No. Well, we know that by adding more wheels or the manifold in the middle actually break the floor, but we think that maybe by putting a track unit, just replacing the track unit, we don't have to put
The 4 wheels.
4 wheels.
Okay. You can try.
Yeah,
See,
try-
there's
we'll try to
new chassis design,
Yeah.
which is without the 4 wheels. Without that, can be, a whole load can be sustained. Okay. So the next is group C.
Sir.
Have you seen the MR?
Ah,
No?
but I thought so much of it, so like whenever I close my eyes, I can see, yeah,
Imagining that.
yes, I can imagine.
But that is physical AMR. You can go and have a look for it.
Yeah, it's pretty big, yeah, like it's bigger than the stick.
You can see the
It's-
have you seen?
800 by 700, like it is huge, yeah.
No, but you have seen in the
No, I
Superbike?
didn't find time.
Uh,
Okay, so in the proposal, we said that we are gonna change the gripper, but like eventually we decided that just the gripper is not enough, and it's not really the thing that we're looking for because it's not a big change. So I talked to the professor, and he said that they wanted to redesign the robot in order for it to work with heavier rolls. So the previous model was designed for 50 kg rolls, and for 10 kg rolls, sorry. And this one we tried to design for 50 kg. So the thing is, we redesigned the entire horizontal axis, which is on this base plate. And as you can see, here we have the moving part, the dovetail horizontal axis on which the moving part moves. And also we have a worm gear to ensure the moving of the moving part. Yeah, that's one later slide. So yeah, and also the previous generation was a bit redesigned with safety factors being so high, and I think that it was also very complicated with that. I'm not going to show it on the picture, but you know there is that what do you call it, like bolt screw?
Yeah.
Bolt screw, yeah. I think it's complicated because it's hard to maintain, yeah. Like it has many parts, and we decided to switch over to a worm gear. I don't know how will it work in practice, but I think it's easier to maintain at least. Okay, so this is the moving part with these dimensions. Nothing spectacular, I believe. So here we have a very big plate on which the gripper is mounted. I think it's around 35 millimeters in thickness. And we have these side walls with triangular holes for weight reduction in it, and then nut for the worm gear. This is the base plate with a dovetail. So the base plate hasn't changed at all compared to the previous generation. We just like redesigned it for our purposes. So these are new holes in it, and also the dovetail mounted. Yeah, it's pretty thick, so I think it can withstand the weight of the moving part with 50 kg rolls mounted on it. We'll show that later. Okay, so I think that's for the design, and I will let my group mates tell you about the analysis that we did.
Yeah, so for the force condition of analysis, we used remote force on the 3 holes where the gripper will be mounted, and then we placed a 500 Newton load where we think the center mass of the printed circuit roll will be. So on the left side is the version 1, and on the right side is version 2. Version 1 only has less side supports with only one singular triangular truss, while the right side has more of a bridge-like truss. So this is the simulation for the von Mises stress, and this is for the maximum principal stress, and then the total deformation. And then for the data, the von Mises principal stress at the maximum von Mises stress for the before, the original design and the version 1 is more or less similar with also similar safety factor, while for version 2 with more support, it creates more safety factor while also reduces the maximum von Mises and principal stresses. It also reduces the deformation significantly. And we also set the material the same, which is aluminum alloy with a yield strength of 469 megapascal.
Yeah, sorry, a quick remark. So you can see that our final design, the version 2, has very high safety factors. So we still have that space for weight reduction. So we decided not to do it just yet, so we can finalize other aspects of the design, and then we can proceed for the weight reduction.
So you will use the same plate? Will be the same?
Yes.
And so how is the plate movement up and down will be using, you are telling about, will not use the screw, you will change it to worm gear.
Yes.
The plate to move up and down.
No. For the moving part, like
Only
this, we're not changing the vertical axis.
You are not changing that axis.
No,
that axis is because by the screw.
Yes, yeah, I think it
The
was
linear
like
screws, yeah.
Yeah, but we didn't touch that at all.
You are done. You
We're
are
only
just taking the gripper part which is going
the
front.
horizontal axis.
Yeah.
Yes, that's it.
We're going front and back.
Yes.
Okay. So you are changing whole part of that.
Yes.
And you
Okay, so I'm gonna talk about the base plate. This is not gonna be the complex part actually. As we said, we're not gonna change anything, so we based on the same thing as the paper, but we just changed it with our design. So we basically here we have done kind of similar to before. So we estimate that the load of the overall is gonna be about around, we use 1,000 like a point load to test if the basically can withstand with it. So this is the this is stress for the test design. Okay. Here's the maximum principal stress. Spectral. And total deformation, of course, you can see that the load withstand can cause the maximum stress in the middle. Yeah, and just from the paper, and then this is our safety factor for the our design. As you can see, it's a bit smaller. Yeah, and for the aluminum alloy, we use the same as before, and as I said, it's 1,000 remote, 1,000 Newton remote load.
And for the conclusion, we have the version 1, we have the similar result, like the safety factor is similar to the original design, and version 2 have higher safety factor, so we can do other like to simplify the design. And the base tech, we have lower safety factor, so it will like the problem we have.
It is lower, but it is still okay. Yeah.
So it's not over design.
It's not over design in this.
Like, right, that was over design.
Ah?
The previous our model was over designed.
Yeah. So
we have a take off to be very high.
yeah, we analyze base plate with the dovetail in it, so it adds up to the sturdiness somehow. Yeah. So because
in the last year DMC class, we proposed that base plate should have like to reduce the weight. That you have used like some honeycombs.
we can do that. We can do that as well. We can do that as well. We still have time. We still have like space for imagination. Yes. So I think we will reduce the weight as much as we can because we still have space and the means for it.
But what about the actuation, front actuation and?
This is still to be worked on. So if you could see the model, yeah. So I left that space blank just yet. So yeah, I think we'll have to calculate some kind of electric motor for it to move. Yeah, because there was some kind of motor used in the previous design. Yes, so I think we'll just calculate the motor for this.
And the gripper to grip the roll will be the same? Or you thought about something new on that?
I mean, like, if the previous gripper can comply with requirements for 50 kg rolls, we'll use it. If it's not, then we'll look for a new option. Like no matter.
No, the diameter of the roll will be the same. The thickness will be increased.
Yeah.
Of course.
Yes.
Inner diameter will be the same.
Yeah. I mean, but grippers have also their limits. Yeah, if the previous gripper can withhold 50 kg unit, I don't mind using it because if it's like if it's already tested and it has it already exists,
that's why I suggest you to have a look once.
Yes, I will for sure. I've been busy, so I couldn't.
Okay.
What do you think? Yeah.
Go through it and find something more interesting on it. So I think all the presentations are over. Any questions which you have? No? I can suggest the other two groups can at least have a look on the AMRs, which is at Industry 4.0, and the CubeSat. already I've given you the suggestion to finding something new for the deployment, like using origami. So it can be reduced your actuators which are placed inside the unfolding of the solar panels. Okay, thank you very much.